Rao, sir.
Hello, am I audible, ma'am?
Ye-
Hello,
Yes,
Hello.
sir. Yes, sir.
am I audible?
Yes, sir. Yes. Shall we
Yeah,
start
yeah,
this?
yeah. Can you share the screen and start?
Okay, okay.
Okay, thank you.
So, good afternoon, everyone. So, welcome you all for this insightful session as part of our ongoing faculty development program on next generation health technologies organized by Department of Electronics and Biomedical Engineering at Adi Shankara Institute of Science and Technology in association with Telemedicine Society of India, Kerala chapter. And today, actually, we are delightful to have us with the Dr. Yedukondala Rao, a distinguished academician and researcher whose expertise lies at the intersection of signal processing, artificial intelligence, and biomedical systems. And Dr. Rao is currently serving as an assistant professor at NIT Puducherry, and he brings with him a rich blend of academic rigor and international research experience. And he recently completed his postdoctoral research fellowship at prestigious University of Connecticut, USA, where his work focused on applying signal processing and AI to healthcare application. And he earned his PhD from IIT Madras, and also he completed his master's in VLSI from Pondicherry University and his bachelor's in electronics and communication engineering from Acharya Nagarjuna University. And Dr. Rao's professional journey spans premier institutions such as Manipal Institute of Technology and Vellore Institute of Technology. And his core competencies include MATLAB, Python, Verilog, and FPGA-based digital design with a deep interest in wearable electronics, emotion recognition, and analog digital system integration for healthcare. So today, he will be sharing his expertise on the topic EDA and emotion recognition. So let us all give a warm virtual welcome to Dr. Rao, and I now invite him to take over the session. And over to you, sir.
Yeah, thank you very much, ma'am, for the introduction. And thank you for inviting me to the talk in this FDP. I'm honored to be part of this program. So let me share my screen. So can you see my screen, ma'am?
Yes, sir. Screen is visible.
Okay. Okay. Okay, good afternoon, everyone. Ma'am has already introduced me. I'm Dr. Yedukondala Rao, currently working as an assistant professor at NIT Puducherry. The topic today, I'm going to deliver a talk on electrodermal activity and emotion recognition. I think other experts might have talked already about the other physiological signals and emotion recognition in the morning session. So today I'm going to give a talk on how to use electrodermal activity signals for detecting the emotion of human beings. Okay. So this is the outline of my presentation. So first I'm going to give some introduction about what is electrodermal activity and the origin of electrodermal activity, the pathway of brain to dermal activity. And then the database we are going to work, then decomposition of EDA signal, some signal processing techniques I have used, then the feature extraction, classification of emotion, finally the conclusion. So we start with the definition of the emotion. So emotion is a complex term. So it is very difficult to define it. So emotion is basically defined in three ways. That is, let me point it, yeah, in three ways. So we can define it in the physiological way and how the user is experiencing the emotion or how the user is behaving during the emotion. So these three are the main components of emotions. We are going to use it. Okay. For example, you take three emotions, happy and sad. Just two emotions you take, happy and sad emotions. Both are dichotomous emotions, completely opposite. So if you take a happy emotion, how these components like physiological experience and behavioral are varying, we can see here. So physiological is nothing but how your physiological parameters are going to vary in the happy emotion. For example, your heart rate is going to rise and your bronchi is going to dilute then skin temperature is going to increase, and sweat secretion is also going to increase. So whereas when it comes to sad emotional state, you can see all these physiological parameters are going to decrease. Similarly, if you see how the user is going to experience this happy emotional state, is the decision capability of humans is going to increase, and the person is going to interact more socially, and the creativity of humans also going to increase when the person is very happy. And the sadness emotional state, so all these experiences like decision making capability is going to reduce, and social interaction of a person is going to reduce. The people will not interact with anyone, they just go close the room and sit inside. They don't talk to any other friends also. The creativity of a person is also going to reduce. So there are more implications on these emotional states. Okay. And whereas when it comes to behavioral states, the cheats, behavioral state is nothing but how your physiological outside appearance of a person is going to change. So when you are in the happy, your cheeks are going to rise, eyelids are going to wrinkle, and teeth are exposed when you smile, and lip corners are also better. So when you are sad, your lower lips pours out, eyebrows ends up, jaw comes up, and then lips corners are also going to be down. These are just two emotions, how the physiological parameters and how the subject is going to experience and how the behavior of the person is going to change. So there are many emotions. So we are going to, in this talk, we are going to see how to detect these emotions. Okay. So emotion is very complex because it depends upon all these components such as physiological experience and behavioral. So defining emotion is very complex. Okay. So let us see how to understand these emotions. So emotions can be positive or negative. So in the previous slide, we have seen like happiness and sadness. Happiness is an example for positive emotion, and sadness is an example for negative emotions. So we have set of emotions. All these emotions, we can say some of them are positive emotions and some of them are negative emotions. When the person is experiencing the positive emotions, so you will have a quality, like improvement in the quality of the life, and productivity in the work also increases, and interpersonal functioning, like communicating with others. Social skills are also going to increase when the person is having a positive emotion. If suppose a person is having negative emotions, for example, sadness, stress, depressed, so these are examples for negative emotions. And positive emotions are joyfulness and happiness are the examples for positive emotions. When the person is experiencing these negative emotions, so you'll be depressed and anxiety will increase. And the depression and anxiety are the major causes of the death worldwide, as per World Health Organization. Okay, quantification of these emotions, especially this depression and anxiety, are very important. And this is very intense area of research because this is causing a major death worldwide. Okay. And then emotional state analysis. So these emotional state. So, hello. If we can detect these emotions, so we can predict the diseases such as depression and anxiety very early, so that we can take a proper action. So for that, we need to go for emotional state analysis. So by using this emotional state analysis, we can identify all these disorders which we get during the negative emotions can be identified in the early stage, and we also can improve the diagnosis. Okay. The main components of the emotions are physiological arousal, subjective feelings, cognitive process, and behavioral direction. So these things we have already seen in the previous slide. So let us see how to describe the emotions. So emotions are basically, we can divide broadly into discrete and affective dimensional approach. So discrete is nothing but there are 6 basic emotions. So you can see here, joy, fear, disgust, surprise, anger, sadness. We just represent only 6 basic emotions discretely, individually. Joy is different, sadness is different, fear is different, disgust is different. So this kind of representation And detecting these kind of only 6 emotions is called as discrete emotion approach. Okay. So when it comes to affective dimensional approach, we can classify multiple emotions, more than 6 emotions we can classify. So by if you use only the discrete emotion approach, we can classify only 6 emotions. For example, you see here, so in the affective dimension approach is a 2D method. X-axis represents valence and Y-axis represents arousal. So here we can map all your emotions. So for example, if we take alert, excited, elated, happy. So all these emotions comes under high arousal and high valence. This is also called as high or pleasant experience of the subject. So all these emotions comes under high valence and high arousal. Okay. When it comes to sadness, depressed, bored, all these emotions we can categorize them into low valence and low arousal emotions. Okay. Here the arousal is nothing but the intensity of human emotion felt by the subject. Similarly, the valence is nothing but the emotion, whether it is a positive effect or negative effect, the user really feels is called as valence. That is, it can be high valence or negative valence, or we can also say pleasant valence or unpleasant experience. Okay, so in this talk, we are going to classify these emotions, like the dimensions. So if you take only this discrete emotional approach, we are going to detect only 6 emotions. So that we are going to take this affective dimension approach so that we can detect multiple emotions. But here we are going to detect only the dimensions, that is high arousal, low arousal, high valence, and low valence. So how do you measure these emotions? Emotions can be measured by using non-physiological or physiological approaches. So, for example, non-physiological approaches include facial expressions, speech, and body gestures. All these methods comes under non-physiological. So the physiological experiences comes under EEG, HRV, HRV, EMG, and EDA. So the main difference between them is, so non-physiological types are easily controllable. So for example, if you are sad, maybe you can change your facial expressions and you can pretend like you are happy. Okay. So this is not a genuine emotion. Even speech also. So when you are in the sadness, usually your voice shivers, but you can control that. Okay. But whereas when it comes to physiological emotion, physiological signals such as EEG, HRV, EMG, and EDA, you cannot really control yourself because these responses are obtained from autonomic nervous system that is controlled by the sympathetic nervous system, SNS activity. So you are going to record these signals from the sympathetic nervous system activity. So these are not easily controllable, okay, because they are involuntary. So the emotions obtained by using these signals are genuine from the subject. Okay. So since we have a lot of physiological signals to detect emotions, but in this talk, we are going to see how we can detect emotions using the EDA only, because EDA has some advantages, like the instrumentation of EDA is very small and it takes very less number of electrodes also, and it is very much suitable for the wearable applications. That's why we are choosing EDA, electrodermal activity. When it comes to EEG and other physiological signals, the instrumentation is very complex. So that is the main advantage of EDA. Okay. So let us start with how to detect the emotions using electrodermal activity signals. So let us see what is this electrodermal activity. So EDA is nothing but it's a measure of changes in the electrical conductance of the skin, which changes in relation to eccrine subgland activity. So it is nothing but changes in the skin, changes in the conductance on the skin is detected when the emotion is rising or falling down. Okay. So this is the pathway of emotions. You might be wondered how we can detect emotions from the electrodermal activity from the skin directly, because emotions are induced in the brain. The emotion starts in the brain. So this is the pathway of emotion. Okay. Emotion starts in the amygdala. Amygdala is the emotional center. Okay. So it starts here and then it passes through anterior cingulate cortex, and then it stimulates sympathetic chain ganglia via ventral horn. So this is the pathway of emotion. Starts in the amygdala, then it goes to anterior cingulate cortex, then ventral horn. You can see this blue color line, and then sympathetic chain ganglia. So this sympathetic nervous system stimulates adrenal medulla by releasing a chemical called ACH. Okay, so this chemical stimulates these sweat glands. So basically, we can define the sweat glands into apocrine and eccrine sweat glands. So these eccrine sweat glands are responsible for the emotional activity, that is emotional sweat. So these apocrine sweat glands, we also get the sweat from these apocrine sweat glands, that is due to the thermoregulation, mainly due to the thermoregulation and hydration. So this ACH chemical is going to stimulate ADR. ADR stands for adrenaline. So this stimulates this adrenaline, which in turn releases sweat on the surface of the skin. So this is the pathway of emotion. So emotion is induced here. It starts in the brain, but we are going to record in the sweat gland region. That is, on the surface of the skin, we are going to record this emotion. So let us see the physiology of EDA. As I said you in the previous slide, so ADR is going to, this sympathetic ganglia is going to stimulate this adrenal medulla using a chemical that is called ACH, and it releases ADR or NA, ADR and NA to control these eccrine sweat glands. So let us see what happens when the sympathetic nervous system stimulates this eccrine sweat glands. So when this sympathetic nervous system stimulates this eccrine sweat glands, the sweat is produced in this pore region. So these eccrine sweat glands secrete the sweat on the surface of the skin. So it pushes the sweat. When the sweat glands are full, it pushes the sweat on the surface of the skin. So sweat will be accumulated here initially. When the sympathetic ganglia is stimulated, sweat is accumulated here, and then the accumulated sweat will be pushed on the surface of the skin. So sweat on this surface of the skin, so it gives the electrical conductivity because sweat will have a salt content. Because of this salt content, it is going to increase the electrical conductivity on the surface of the skin. So these pulsative effects of sympathetic nerves measured at the skin is termed as EDA, because sweat will be filled whenever you are in the emotion of sadness, something happens. So when you are in the sadness, more sweat will be released here, and it will be released on the surface of the skin. The salt content of the skin is more, the conductivity of the skin also increases. So this is the fundamental physiology of EDA, electrodermal activity. Let us see how to record the signal now. So Toren et al. In 2012, so he experimented and he recorded electrodermal activity from 16 locations. You can see here all the locations like fingers he has recorded. So here fingers he has recorded, and then wrist region, and then central wrist region, then vertical wrist. So this is the vertical wrist, then chest region, uh, foot region. Like that, he recorded. He did an experiment of recording this electrodermal activity on the 16 locations of the body, and he found that only the 3 locations are giving the best results. That is, the first one is at the region of forehead. So we get best electrodermal activity in the forehead region. The second best is in the foot. The third best is fingers here. So these 3 are the primary regions where we can record the electrodermal activity effectively. But practically real-time recording, if you see, recording the signal from the forehead is very difficult. So it is not a suitable position for the real-time applications. Even the foot region, we are going to wear the chappal and shoes. So recording the signal from the foot region is also not a feasible location. So electrodermal activity is mainly recorded during in the fingers only. So this is the optimal location where we can record the electrodermal activity signals. So these are the popular measuring sites. So this is the between the fingers we record. Then thenar and hypothenar muscles. So these are called as thenar and hypothenar. Between these two regions, we can connect the electrodes and record the signals, or between the two fingers. So when you are connecting the electrodes between the two fingers, we have to connect between the medial and distal phalanges of middle and index finger alone. Not we cannot record between any two fingers. We have to record between only middle and index finger, and that too the regions like medial and distal phalanges, either this region or this region, or foot region. So this is not a feasible location. So mainly we connect here and record the signals. So how do you measure? Now we have decided what is electrodermal activity, the physiology, pathway. Now we see the regions also we have seen where to record this electrodermal activity. Now the question is how to measure this. So we can measure this EDA using two popular methods, that is endosomatic and exosomatic. So the difference between them is mainly giving an input. Okay, in the endosomatic region, we do not apply any current into the skin. Okay, instead of we just measure the potential differences originating in the skin. Okay, but whereas in the case of exosomatic, we are going to induce a small amount of current into the between the fingers and then measure the resistance. So once we have the resistance, we can measure the conductance very easily. So inverse of resistance is nothing but a conductance. So first to record the resistance, apply a small amount of current onto the surface of the skin, then record the resistance. So inverse of the resistance is nothing but a conductance. So skin conductance, electrodermal activity is nothing but skin conductance. We are measuring this conductance from the dermal activity. That's why it is called as electrodermal activity. So this is the signal. So we have seen how to record the signal also now. So this is the recorded signal, how it looks like. So this is the EDA signal. You can see here, this is how the EDA signal looks like. EDA signal looks like. So when you carefully observe this EDA signal, so you can see this is the x-axis is timestamp and the y-axis is conductance. So it is measured in the microsiemens. Unit of this EDA is in microsiemens. So this EDA signal basically will have two components. It is a combination of two components. Okay, it is composed of two components. So we can classify them into tonic component and phasic component. Okay, so this has a combination of both tonic component and phasic component. So the tonic component is nothing but a slow variation of skin conductance. So this skin conductance we get because of the thermoregulation of the body, ambient temperature, and humidity. So when you go outside during the sunlight, you also get the sweat. So that sweat is different than your emotional sweat. Both are different. Okay. So when you also get sweat when you go to the sunlight. That sweat is called as tonic component. So when you record the EDA signal, so EDA signal will also have tonic component. Remember that. And the phasic component. Phasic component is a faster variation of the skin conductance, which reflects sympathetic nervous system activity. So during the emotion only, sympathetic nervous system is going to be activated. So when the sympathetic nervous system is active, so you get some sweat. This sweat is called as phasic component. The signal obtained during the sympathetic nervous system activity is called as phasic component. So when you record a signal from the surface of the skin, so it will have both tonic and phasic component. Okay, but this tonic component is useless for us. That is because of the temperature when you go outside. That is because of thermoregulation of the body, ambient temperature, and humidity. So that is useless. Our concentration is only SNS response, recording the SNS response. So we have to remove this tonic component from the EDA signal and obtain only this phasic component. That is the main challenging in this work. Okay, so this is when you separate phasic and tonic component, So the signals looks like this. So this is the phasic component and tonic component. When you see this, you can mainly observe like there is a smooth variation in the tonic component. So that's why it is called as slow variation of skin conductance. So when it is a phasic component, it is a fast variation of the skin conductance. You can see there are some fluctuations. So it is varying very fast. So this is due to the So this reflects the sympathetic nervous system activity, and this reflects thermoregulation of the body, ambient temperature, and humidity. So this is useless for us. So we are going to separate this phasic component from this EDA and try to apply some signal processing techniques and extract some features, apply those features to machine learning algorithms to classify various emotions. So this electrodermal activity is going to change from emotion to emotion. So there are some challenges also when you take this EDA signal. It is not that easy. So EDA signals are very complex because they change. They are not stationary signals, and they are not even linear. Also, they are non-linear. And while recording also, since you are recording from the fingers, so usually you will move the fingers while recording. So it will be affected by some of the artifacts. Okay. Some of these parameters affect the linearity of the signals. So as I said, EDA is a nonlinear signal. So what factors makes the signal to behave like a nonlinear signal? So these are the factors. The first factor is density of the sweat gland. The density of the sweat gland varies from human to human. And the size of the sweat gland is also changes from human to human. So this in turn reflects in the frequency and amplitude changes in the signal. Okay. Also, the sweat per gland and its temporal variability also varies. So this parameter is going to change time varying signal characteristic of an EDA signal. And the output of individual glands also changes. So this is going to change an abrupt changes in the EDA signal. And also, sweat gland or fiber densities. So this parameter will induce complex periodicity in your EDA signals. Also, conduction velocity. This will induce intermittent bursts of the signal. These are some of the challenges we have to go through when you apply this signal processing analysis. And also, since the signal is very non-linear, also EEG signal, EMG signal, all the signals are also non-linear signals. Almost all the signals you record from the human body are non-linear signals because all the systems, human body systems are non-linear systems. So you record the signal from the non-linear systems, you get non-linear signals. So in my work, I tried to apply the non-linear signal processing methods to this EDA signal and classify the emotions using some machine learning techniques. So this is the motivation of the work. The prevalence on mental health disorders has continued to increase, and also it impacts on the socio-economic growth. And the characterization of arousal and valence dimensions using the EDA can help discrimination of emotional states. And if you use, since the EDA signal is non-linear signal, if you use the traditional linear signal processing methods, it may not be sufficient because the signal itself exhibit non-linear behavior. But when you try to characterize the emotions using linear signal processing, it may not be. Sometimes you get the good results, but it may not be sufficient to characterize these emotional states using just linear signal processing methods. So in this work, I tried to use some of the nonlinear signal processing methods to classifying these emotions. So this is the objective as we discussed. So EDA signal will have both phasic component and the tonic component. So our first objective is to remove this tonic component from the EDA signal. So this smooth variation is useless for us. That is because of thermoregulation and humidity of the body. So we have to separate this tonic component from the EDA signal and obtain only the phasic component. So this is a representative signal. And you apply the signal, nonlinear signal processing methods only on this phasic component, not on the tonic component. So these are some of the methods I have used. I quickly go through the signal acquisition part. So how do you acquire this EDA signal during the emotions? So you can record, as we discussed, we can record at thinner and hypothinner. In the laboratory settings, you can record in these regions also. But in the real-time applications, you can connect your electrodes in between the middle and index fingers also. So we have to make the participant in the relaxed condition, ask the participant to sit properly and take a rest for 5 minutes. Then you show the emotional stimuli for a minute. For a minute, you show the emotional stimuli and then record the signals. Any of these three locations I have mentioned. So for this study, I have taken the signals using deep data set. So in the deep data set, the EDA signals are recorded from 32 participants, subject 1 to subject 32. So there are 40 videos we have shown there. The deep database has shown 40 videos and continuously they have recorded 20. After that, they have given a break of 20 minutes, then 21 to 40. Each trial or video will consist of a 2-second trial number initially so that participant will have a sequence which video number he is watching. So for that 2 seconds, they have displayed a trial number of the video and then fixation for us, a 5 minutes baseline recording. Simply, you can ask the participant to take rest and record the signal for 5 minutes. Then you apply the emotional video, that is audio-visual stimuli for a minute. For a minute, you show the video, the happiness, sadness. So you change the videos like that. 40 videos you show there, 40 different videos representing various emotions, and then self-assessment. After showing the emotional video of 1 minute, also you assess the subject. Ask the subject, how do you feel your emotions? Ask them to rate on these scales. Scale is called as self-assessment mannequin, SAM, self-assessment mannequins. You ask the participant to rate their emotions on the scale. So the scale will have ratings from 1 to 9. So initially there is an arrow mark. It is slidable. You can slide this arrow mark wherever you want. Okay, for arousal 1 scale, for valence 1 scale. So if the participant is feeling more arousal, they slide this arrow mark to either one of this region between 5 to 9. The participant is using low valence or low arousal, the participant move between 1 to 5. So if they rate their emotions between 1 to 5, it is either low valence or low arousal. If they rate their emotions between 5 to 9, it is either high valence or high arousal. If it is in the valence scale, it is high valence. If it is in the arousal scale, it is high arousal. So we record the signals. This is how the recorded signal looks like. So, for example, these are the representative signals only. It need not to be the same for all the subjects. I just have taken one subject. If we take the high arousal, low arousal, high valence, low valence, all these signals, how it looks like. Okay. If you see high arousal, high valence, if you see there are more number of fluctuations. So when you compare with the low arousal and low valence. Okay, you can notice for another subject also. This row represents for one subject alone, and this represents second subject. Okay. So variation for both the subjects, the variations are more for high arousal and high valence when you compare with low arousal and low valence. So our first aim is, as we discussed in the previous slides, so we have to separate the phasic component from the tonic component. So for that, we have different methods. So I quickly give the brief introduction because it is very difficult to understand for the given time, 1 hour. Okay. So these are the algorithms. So these are the four algorithms invented by the popular researchers. So Bach et al. Has introduced dynamic causal modeling. In this phasic component are estimated by using a simple linear time invariant system. But if you use this method, you get a little distortion in the phasic component. And continuous decomposition analysis, you can just use a standard convolution. You can use standard convolution here. You can remove the distortion we obtained in the dynamic causal modeling in this, but the problem here is it gives a non-sparse solution. So for removing the non-sparse solution, Greco et al. Has introduced convex optimization based EDA. In this, we can successfully remove this non-sparseness. So by using this method, this also uses dictionary modeling techniques. It uses 2 separate dictionaries, one for phase phasic modeling and another for sonic modeling. It uses the dictionary modelings, and there is no subject interference also here. But only the problem here is some of the parameters for imposing the sparsity, we have to manually induce. So that is a problem that was successfully avoided by using this sparse deconvolution method. But this also has some problem. Sometimes it is going to give over sparse solution. So we cannot, by going through these works, we cannot decide which is going to give best results for separating the tonic and phasic component for the emotions. So what we have done is we have taken all these methods and removed these tonic components, and we have seen the results, how the signals are going to look like. See, you can see here, these are the EDA signals. So all these four emotional dimensions we have taken and showed the examples here. So this is for high arousal, low arousal, high valence, low valence. You can see the four methods are there: CDA, DCM, sparse EDA, CVX EDA. Everywhere you can see CDA, DCM, sparse EDA, CVX EDA. Okay, so when we are visually looking at this one, we cannot find a much difference between all these methods because they are normalized. You can see every signal is normalized between 0 to 1. You cannot find out much minor differences here, but when you actually plot and see in the MATLAB, you can find out higher amplitudes when compared to all other methods. You can find higher amplitudes in the CVX CDA. And also, so low competition time between this CVX CDA and sparseness. And CDA is inducing more sparseness, and these two methods are taking very less time, less computation cost. And DCM is introducing less noise. So it is going to the flux. We have observed some of the fluctuations. Okay. So by visually seeing all these signals also, we cannot say which method is good for separating these phasic and tonic components from the EDA. So we took help from machine learning. So for that, we extracted some of the features. Even the features also, we did not blindly take only time domain or only frequency domain. We have taken some group of features, 3 different groups of features we have taken. The first group is statistical, the second group is morphological, third group is Earth features. So these 3 groups of features we have seen, we have extracted from the phasic component of each method and applied to the machine learning methods such as logistic regression, MLP, and adapters. We have also seen other methods. They're just showing these 3 results. Other methods are showing 4 results. Okay. So we have seen an interesting observation here. You see either statistical group or morphological group or Hazard group. We found that CVX CDA. So this is CVX CDA. CVX CDA is having highest performance when compared to the other methods. Even if you take morphological features, CVX CDA is showing the highest performance. Even if you take Hazard features, CVX CDA is showing highest performance for classifying between high arousal and low arousal. We also have did the same process for classifying between valence, high valence and low valence. So interestingly here, DCM is showing high performance when compared to other methods. But we can observe here the difference between DCM method and CVX CDA is minimal. So it is almost same. But whereas in the case of arousal classification, the difference is huge. There's a lot of difference. Approximately this is 69% and this is 57%. There is a huge difference. So thus we selected CVX EDA is an optimal decomposition method for differentiating emotional states. And then, so our job is over. We decompose the signals. We obtained the EDA signal here, and then we decomposed by using CVX EDA because this is giving better results. Then we have separated. Finally, we got phasic component. Then we tried to apply some of the nonlinear signal processing methods to classify this emotional state. The first one is ISACS method, improved successive approximation method. In this, what we did is, so we took the phasic component and then we separated the phasic component into 6 equal parts. So you can see there are 6 equal parts. Again, each equal part then subjected to PAA. PAA is nothing but PAA is piecewise aggregate approximation method. So we divided this each equal part into 32 segments again. 32 segments. So in each segment, there will be some time points. You can see a window. So we have taken all the time points in this window, small window, and we just took the average of all those time points and represented with a single straight line. Single straight line. And this straight line, in the next step, we have assigned a symbol. So by using discretization, this step is called as discretization. This symbol we have assigned based on some threshold points. We have taken some threshold points, that 0, beta 1, and beta 2. So based on these threshold points, we have assigned a symbol. Hello. So based on this cutoff points, we have assigned a symbols A, B, C, D. If your signal strength is less than this beta 2, we have assigned A. If your signal is lying between 0 to beta 1, we have assigned B. 0 to beta 1, we assign C. So more than beta 1, we assign D symbol. This is how the symbolic sequence of the particular EDA signal looks like. Okay. So in our work, what we have done is, instead of taking just a simple mean value to comprehensively analyze this phasic component, we have taken the other features also, multiple features. Instead of just taking mean, so we have taken mean of the negative values of first order derivative, mean absolute value, temporal moment, max, dynamic range, activity, mobility, complexity, chaos, and hazard. Many features we have taken. You can see, we can observe there is a difference in sequence also. So some of them are not varying much, but some of them are really varying. So we are getting some valuable information. So we have taken these symbolic sequences and then applied a sliding window method. We applied a sliding window method. Sliding window method is nothing but you choose a symbol and you find probability of occurring the next symbol also A. Or you take the symbol and find out the probability of occurring next symbol is B. Also, you take a symbol A and find out the probability of occurring the next symbol C. Like that, you obtain all the probabilities for sliding window length 2, or you take the two symbols also, group of 2 symbols. In this case, you can read this one as like, take AA, initially AA, and see the probability of occurring third symbol A, and the probability of occurring third symbol B, third symbol C, third symbol D. Like that, we have obtained all the probabilities. And we calculated this by using this formula, symbol bit string by n minus the length of the string minus sliding window length plus 1. By using this formula, we obtain these probability values. From these probability values, we extracted the few features, that is the Renyi entropy, Salis entropy, Shannon entropy, and then modified Shannon entropy. We have not shown all the results here. This is just a simple example of how Shannon entropy is varying. There is no much variation for this feature. So mainly we identified like mean of F6. F6 is dynamic range, and F9, F11 are varying. F11, F11 are nothing but they were Hazard features. So we found like Hazard features are more sensitive for differentiating these emotional states when you use symbolic aggregation approximation method. Okay, and since we identified only Hazard features are very well significant for differentiating these emotions, we also have seen how these Hazard features are varying for different ratings. In initial slides, I have explained how they have recorded the signals and how the self-assessment of these emotions has been taken from the participant. Okay, so the ratings are also seen. The ratings are also varying. Shannon entropy of the ratings between A to B. Here A to B represents 0 to 1, 1 to 2, 2 to 3, 3 to 4, and up to 9. The ratings are varying from where. You can see a significant variation in the ratings of the participants also. Also, we have seen how Shannon entropy is varying for all the 40 videos. There are 40 videos we have recorded from the 32 subjects. You take one subject and how the Shannon entropy is varying for 40 different emotions. We have observed like there is a huge variation in all the videos. So Shannon entropy feature is able to detect the emotions clearly. So these are the results. We have used a random forest. Once we obtain the features, these features we subjected to different machine learning algorithms. We obtained highest performance using rotation forest algorithm, ROF, rotation forest. So interestingly, So we have observed here highest FM score. FM score we found for a symbol size 4. Symbol size 4 represents here. We have used 4 symbols, that is A, B, C, D. We can use the ABC symbols also, but in our work we have used ABCD symbols. For when you use 4 symbols, and also the sliding window length also we have changed 2, 3, 4. The sliding length is 2 and the symbol size is 4. We have obtained a maximum performance for arousal differentiation. Similarly, for valence differentiation also, we have obtained a maximum performance when the symbol size is 4 and sliding window length is 2. So thus, for emotion classification, we decided that sliding window length 2 and symbol size 4 are the optimal values. So further, if you are working on any of the ASIET methods, you can directly start with L equal to 2, alpha equal to 4 for your studies. Also, we have extended our study for the smaller length of the signals. So instead of taking the 1 minute length, so what we did is, for reducing the computation, especially for variable electronics, it is very useful. So what we did is, instead of analyzing whole length signal, we took only 15 minutes and repeated the analysis. And 30 minutes repeated the analysis, 45 minutes, 60 minutes, we repeated the analysis. So interestingly, so we obtained the similar results of full length signal at 45 seconds itself for arousal classification. And we obtained the similar results of this full length signal for just 15 seconds of the signals. Instead of taking all the signals, we just obtained the similar analysis, similar results for 15 seconds of the signals, so that we can use this method for variable applications, especially where the computation time, where the less computation time is required. So that is one method. And the second method, we also use like symbolic transition networks. This is also one of the advanced nonlinear signal processing methods recently have been used. So in this phasic component, all the points have been considered here, and we segmented the signal into some equal parts. So depending on the length of the signal, this is what we did in our study is, so we just took the difference between the neighboring points, adjacent data points. So we have subtracted this value from the previous value and this value from the previous value, this value from the previous value, and obtain the values here. If you get a negative value, we represented that negative value with a binary 0. And when you subtracted these two values, if you get a positive value, then we represented that value with a 1, either 0 or 1. We got a binary sequence here. Again, this binary sequence, we converted to a decimal sequence with just 4 symbols, that is 0, 1, 2, 3. Okay, so that we did by grouping only 2 binary digits. By grouping only 2 binary digits in the binary sequence, we obtained the decimal sequence. Now what we have done is, we calculated the probability of obtaining the transition between 0 to 1, transition between 0 to 0 to 3, and 1 to 0, 1 to 2, 1 to 3. Similarly, 2 to 3, 2 to 1, 2 to 0. All these transitions we have obtained, and this is how it looks like. So these are symbolic transition networks we found out, and this is for the first 2 signals are for arousal, and next 2 signals are for valence. And this is the binary sequence we obtained after subtracting the neighboring points. And then from this, we calculated the probabilities from all the transitions of the decimal sequence. So we have seen some interesting results, like some of the transitions are making the difference between high and low arousal. You can see here there is a transition from 3 to 6 that is missing here in the higher arousal. Also, there is a transition between 3 to 0. 3 to 0, there is a transition here, there is no transition. And 3 to 6, there is a transition, there is no transition here. Similarly, for valence also, there is a transition from 4 to 1, that is missing here. And 1 to 6, that is missing here in the high valence. And transition between 5 to 6, 5 to 7, and 7 to 5, vice versa. So both transitions are missing here. So there is clearly, you can see that there are some transition differences. There are some transitions which are missing between high and low valence and high and low valence, or high and low arousal. So we can make use of these transitions existence. This is not the end here. We have to extract some of the features from these networks, from the nodes, each of the nodes, and pass these features to the machine learning algorithms to classify the emotions. So we have selected some of the features and obtained these values by using MLP classifier here. You can see So we have seen both motif 2 and motif 3. This is an example for motif 3. Same analysis we continued for motif 2 also. Interestingly, for motif 3, we obtained good results for both arousal as well as valence. So motif 2, we obtained slightly less performance when compared to motif 3. Maybe if you go for motif 4 and 5, we may get better results, but we did not do that analysis. If you want, you can try that. Also, we explored the use of two more advanced nonlinear techniques, nonlinear signal techniques, that is time frequency spectrum, EFCDM, and then complex plane boundary detection using geometric features. So in this, what we did is in the time frequency spectrum, so we obtained only the time spectrum from the signal, which is the range of 0.05 mega, 0.05 to 0.25 Hz. So only this frequency is very sensitive. Sympathetic nervous system is very dynamic during these frequencies. We already know that. So since the sympathetic dynamics are more during this frequency, so we concentrated, we have separated only these frequencies. Okay, and then obtained, we reconstructed the EDA by using these frequencies, and then calculated the Hilbert transform and got this signal. From this signal, we also got the TV SIMP. TV SIMP is nothing but time varying sympathetic activity that we obtained using this instantaneous amplitude calculation. Also, MTV SIMP, modified TV SIMP, we obtained by subtracting this value 80, that is TV SIMP, from the max value of the signal. Also, we have seen the geometric method. In the geometric method, we have taken the 1D signal and converted into 2D signal by applying into DTFT method. When you represent a signal using DFT method, we get real value as well as complex value. The real value, complex value is nothing but a 2D representation of a signal. Okay, from that signal, the boundary of all these complex conjugate values are obtained by using the alpha shape boundary method. From that boundary, we have got few features and then applied those features to the machine learning algorithm. I show the pictorial view how this VFCDM works. In the VFCDM, this is how the signals look like: high arousal, low arousal, high valence, and low valence. So you can clearly see from the time frequency diagram, only during the frequency less than 0.2 Hz, you can see this is red color. That is sympathetic dynamics activities are high at 0.2 Hz, less than 0.2 Hz. So we collected only these two frequencies and reconstructed the EDA back. Now your new EDA is these signals. So from these signals, we calculated some of the features and then applied to the machine learning algorithm for the classification. So these are some of the values we obtained. I'm not going in deep. So one more method, as I mentioned here, is like geometric features. So this is also one of the advanced nonlinear signal processing method. This what we do is this EDA signal you take and represent this 1D EDA signal into 2D by calculating the DFT coefficients. So get the real time as well as imaginary real time coefficients here. And boundary of all these coefficients you obtain by using alpha shape method. There are different methods for detecting this boundary. In our work, we just have applied alpha shape method. There are different methods. You can try other methods as well. So obtain the boundary of these methods and then calculate the features like convexity, rectangularity, all these features. And then interestingly, we have seen like the geometric features are performing, they are giving highest accuracy when compared to the other methods in our study for emotion classification especially. So this is the conclusion. Like we have seen EDA signals, how to obtain the EDA signal, the physiology mainly we have discussed, and why we are applying the nonlinear signal processing. And we also have seen some of the nonlinear signal processing methods. So like ASIETs. In ASIETs mainly we concentrated to find out the fluctuations in the EDA signal to obtain the arousal and valence, and then time varying spectrum using VFCDM method. It is the time frequency method, time frequency spectrum we have obtained. From that, we reconstructed the EDA signal back. From the reconstructed signal, we obtained some of the features, time varying features, statistical features, and then Hazard features, all those features. Each features we fed to the machine learning approaches for the classification. Same transition network entropy variations we have seen, and this is the feature scope. So same kind of methods we can apply for other complex visualizable signals also. These techniques are used for EDA signal. Maybe if you are working on EMG signal or EEG signals, maybe these methods you can apply for other complex physiological signals also. And also we can, since the methods which I have used here is ISACs and symbolic transmission network, these techniques mainly use it for reducing the computation time. Okay. So which are essential for wearable applications. So nowadays, anything if you take, they're trying to implement using wearable devices, even for emotion detection also. So these methods especially used for wearable devices, maybe for the real-time applications, we can try this. That is one of the future scope of this work. Also, multi-dimensional analysis of EDA. So along with EDA signals, maybe you can see how to combine this EDA with EEG, EDA with PPG, EDA with heart rate, EDA with skin temperature. You can see multiple signals. We can combine them, apply the same methodologies, and see how the performance. So now in these methods, I'm obtaining up to 75, 78%. So maybe we can apply this multimodal analysis method and see whether we can improve these performance further or not. Also, you can use deep learning methods. So we can use these deep learning methods like we are using a spectrum, especially this VFCDM time frequency spectrum. Maybe these spectrums we can apply to the various recent deep learning methods. Like there are very recent deep learning methods like spin transformer is there, mobile net is there. We can try to apply these time frequency spectrums to these deep learning methods and see whether we can improve this classification performance or not. So these are some of the differences. And thank you very much for the attention. If you have any questions, you can talk to me.
So thank you, sir. And now the session is open for any queries. Session is open for audience for any queries. Sir, I have some queries with you.
Yeah, please.
So, like how accurate this EDA is for detecting emotions when compared to other methods? So, like, what are the main factors that affect this EDA reading?
EDA reading, as I told you, it is more non-linear, person to person. So like if you see sweat gland variation, number of sweat gland present on your fingers and my fingers are different. So that is very challenging task. So we are trying to find out how to avoid that problem as of now. But
Like,
still, we are getting when we compare our results with EEG, whereas when you take EEG signal, it directly reflects the temporal variation of brain. There is a delay when you collect from EDA. There is a delay between EEG signal and EDA signal. That is also we are trying to address. These are the challenges. Like
okay, so
variation.
how long actually it will take to get a useful EDA data? How long it will take?
It's milliseconds, microseconds. So that real time we cannot find so much delay. Real time, it's an eye blink time. We can say it is an eye blink time.
Okay, so and one more query is there. You have told that like we can use many deep learning models for to develop this particular system. Like, so whether this learning models trained on this EDA data can be generalized across the people, or it should be personalized. How
No,
it will work?
it can be generalized. Personalized will be more easy, because we are going to take the signals only from one participant and take the significant features and generate the model, like to design the model. Okay, if you want to generalize this, we have to collect at least 1,000 subjects, EDA signals, and then send it to the deep learning models.
Okay, so how this kind of environmental conditions like temperature, many factors will be there, like temperature, humidity,
So
or
that
they
is
affect this. Yeah.
that is the biggest advantage of using this EDA, because we are going to separate the phonic components. Real-time applications, anywhere you can use any environmental condition, you can obtain this EDA signal.
So currently we'll be using sensors. Like, so what kind of sensors we'll be adopting for this one?
So there are many sensors like Fitbit. Have you heard of Fitbit sensor? Or laboratory environment, you can use BioPack device directly.
So all
Or
these
there
are the
are
sensors that
many.
we are using in this kind of wearable device, right?
Yes, yes. And you have the watches also. Watches are
Okay.
also available. You can directly connect a watch and record the signals. That is one thing. And nowadays the rings are also coming. Like
Okay,
if you
so
just
definitely.
wear a ring, yeah, you can just
Okay.
wear a ring and obtain the signal.
So it is actually we are monitoring the emotions of a particular subject, right? So
Yes,
definitely
yes,
there will be some kind of ethical concerns for getting this particular
yes,
signals
yes,
from
yes.
a subject.
Yeah,
So
yeah.
what are those ethical concerns we want to consider while we are doing it
We
in a
have to,
particular
yeah,
workplace?
we have to consider this ethical concern. Definitely have to take it because it's not like just recording these signals. That is first thing. We are inducing the current also. So we
Okay.
are inducing some current onto the skin and then getting the EDA. So everybody will not allow that. That is one challenge. And second thing is, so we have to take the precautions. There are some standards, IEEE standards. We have to take some precautions. How much current you have to obtain. So device you are using for the device you are using for recording must be FDA approved. Because if there are some leakages or something, there may be a chance that more current can flow into your skin. So that will damage your sweat glands permanently.
Okay.
So we have to be very careful when you are recording the signals. And ethical committee approval is compulsory. So ethical committee has to see how much current you are passing and whether your device is FDA approved or not. Everything you have to check it.
Okay. Okay. Thank you, sir. Thank you, sir, for your response. Any more queries from the audience side? Any more queries? So hope we don't have any more queries. So thank you so much, Dr. Rao, for that
Thank you.
insightful and engaging session. And on behalf of the organizing committee of FDP on Next Generation Healthcare Technologies, conducted by Department of EB, Adi Shankara Institute, I extend our heartful thanks and appreciation for your time, expertise, and thought-provoking presentation.
Thank you, thank you, thank you. Thank you for this invitation, and I am very honored to be part of this program.
Okay,
Thank you very
thanks,
much.
thanks a lot, sir. And also we
Thank
thank
you.
all the participants for their active involvement. Let's carry forward the knowledge into our teaching, research, and collaborative explorations. Thank you once again for all.
Thank you very much.
Okay, so we are
Can I leave?
winding up the session. Yes, sir.
Can I leave, ma'am? Or
Yeah, sure. No issue. You can leave, sir.
thank you very much.
Okay, so we are winding up the session. Thanks everyone for listening.